Before diving into VSEPR theory, we first need to learn how to draw a Lewis structure. This is because to figure out the 3D shape of a molecule, we must start by drawing its 2D layout. The very first thing to do is to check the valence electrons of the atoms. Shall we take a look at the video on the screen? Among the electrons orbiting the atomic nucleus, the ones in the outermost shell are the ones that participate in chemical bonding. Figuring out the number of these electrons is the first starting point. Carbon has 4 valence electrons and oxygen has 6. Now, let's look at the process of forming the Lewis structure for a carbon dioxide molecule. The central carbon has 4 valence electrons and the 2 oxygens on either side have 6 each. The carbon and each oxygen provide 2 electrons each to share 2 pairs of electrons. A double bond is formed on both sides and the electron pairs, represented by dots, change into 2 solid lines, completing the 2D Lewis structure of carbon dioxide. At this point, the double bonds formed on both sides of the central carbon atom are each treated as a single electron domain. Therefore, there are a total of 2 electron domains around the central carbon in carbon dioxide. Now, let's analyze this 3D structure using VSEPR theory. The core of VSEPR theory is that electrons strongly repel each other. Electrons, which all carry a negative charge, try to stay as far away from each other as possible. The distancing is what determines the final shape of the molecule. It's just like people moving apart in an elevator. The 2 electron domains will also stand as far apart as possible. As you can see in the video, the 2 electron domains end up positioned on exact opposite sides with the central atom in between. As a result, carbon dioxide forms a 180-degree angle, resulting in a perfectly straight, linear shape. In conclusion, VSEPR theory is simply about determining the number of electron domains using a Lewis structure, and then predicting the shape of the molecule based on the principle that these electrons will try to stay as far away from each other as possible in a confined space. Now, let's look at the molecules with 3 electron domains. When a central atom forms 3 bonds with no leftover electrons, the 3 electron domains push each other away with equal force. They lie flat on a plane to form a trigonal planar structure. Here, the bond angle is maintained at exactly 120 degrees. But what if the central atom has 2 bonds and 1 lone pair of electrons? It still has 3 electron domains, but the situation is different. The lone pair takes up a massive amount of space and presses down hard on the bonds on both sides. As a result, the bonds are pushed downward, forming a V-shaped bent structure. The bond angle shrinks to less than 120 degrees. Next is the case with 4 electron domains. When 4 atoms bond to a central atom with no lone pairs, they stretch out into 3D space to complete a perfect pyramid called a tetrahedral structure. The bond angle here is 109.5 degrees. If one of these domains turns into a lone pair, the heavy pressure from above squishes the remaining 3 bonds. This forms a trigonal pyramidal structure, and the angle becomes narrower than 109.5 degrees. If the lone pairs increase to 2, the repulsive force gets even stronger. The 2 remaining bonds are sharply bent into a bent structure again. The bond angle shrinks even further. When the electron domains increase to 5, they form a trigonal bipyramidal structure. 1 point straight up, 1 straight down along the axis, and 3 spread out across the middle plane. Because of this, 2 different angles exist at the same time, 90 degrees and 120 degrees. If lone pairs appear here, they always take the roomier spots in the middle plane first. With 1 lone pair taking up a spot in the middle, its massive size pushes against the remaining 4 bonds. The 2 vertical bonds act like the plank of a seesaw, while the 2 horizontal bonds act like the pivot. This creates a seesaw structure, and the bond angles are squeezed to less than 90 and less than 120 degrees. When we have 2 lone pairs, they take up 2 spaces in the middle plane. This leaves only 1 horizontal bond pointing out to the side. The horizontal bond meeting with the top and bottom vertical bonds, perfectly resembles the letter T. This forms a T-shaped structure, and the heavy pressure from the lone pairs squeezes the angles to slightly less than 90 degrees. If the lone pairs increase to 3, they take up the entire middle plane. Because these 3 bulky lone pairs push equally in all directions along the flat middle, their forces perfectly cancel out. Only the top and bottom bonds remain, giving us a straight linear structure with a perfect 180-degree angle. Finally, let's look at molecules with 6 electron domains. These form a perfectly symmetrical octahedral structure: up, down, left, right, front, and back. Every single domain maintains an exact 90-degree distance from its neighbors. If one lone pair takes a spot here, it acts like a giant invisible balloon pressing from the bottom. It pushes the remaining 5 bonds upward and outward. 4 bonds create a flat square base and 1 point straight up, forming a square pyramidal structure. Due to the strong pressure from the lone pair, the bond angles shrink to less than 90 degrees. However, if there are 2 lone pairs, the situation changes. These 2 bulky lone pairs want to stay as far away from each other as possible. So, they take positions on completely opposite ends, top and bottom. The strong pushing forces from above and below perfectly cancel each other out. The remaining 4 bonds lay perfectly flat in the middle, forming a neat square planar structure. Because the pressure is equalized, the bond angle returns to a perfect 90 degrees.